Today in Chapter 4, Section 3, we're going to be working with properties for logarithmic functions so that we're using logarithms to simplify and solve. Make sure you have your calculator handy. We won't be able to use our calculator on all of them, but we will on some. Remember that logarithms are our inverse functions for the exponential function. This means that the properties for logarithms, or the rules for logarithms, are going to be related to those rules for exponents. We have three basic rules for exponents, and we're going to review those right now: our product rule, our quotient rule, and our power rule. We have equivalent or very similar three rules for logarithms. With our exponential functions, for our rules for exponents, our product rule says that when we are multiplying the base, we add the exponents because multiplication pairs with addition. For example, in general terms, b to the m times b to the n is the same thing as b to the n times n, or 2 cubed times 2 squared is going to be the same thing as 2 to the 3 plus 2 is my exponent, or 2 to the 5th. Now, if I want to verify that, 2 cubed is 8, 2 squared is 4, and 8 times 4 is 32, which is the same thing as 2 to the 5th power. Okay, my quotient rule for exponents. When I'm dividing the base, I subtract the exponents because division pairs with subtraction. Division is just repeated subtraction. Now, when I'm subtracting, order matters. So you have to make sure that you do numerator divided by denominator, means I take the exponent from the numerator and I subtract the exponent in the denominator. So 2 cubed divided by 2 squared is the same thing as 2 to the 3 minus 1 power, or excuse me, I got ahead of myself, 3 minus 2 power, or just 2 to the first, which is 2. Just to verify, 2 cubed is 8, 2 squared is 4, and 8 divided by 4 is 2. Then I have my power rule. The power rule tells me that when I raise an exponent to another power, I'm going to multiply the two exponents, because raising something to an exponent is repeated multiplication. For example, in general terms, b to the m raised to the n power is the same thing as b to the n times n, or 2 cubed squared, 2 cubed being squared, is the same thing as 2 to the 3 times 2, or 2 to the 6th, which is, if you use your calculator, or we know that 2 to the 5th is 32, 2 to the 6th is going to be 64. Just to verify, 2 cubed would be 8, 8 squared is 64. So if I only have a single base, I'm multiplying the exponents. If I'm multiplying bases, I add the exponents, and if I'm dividing the bases, I subtract the exponents. We're going to use those rules for logarithms to help us expand and contract, or expand and condense our logarithm statements. Now, sometimes when we expand and condense, we're able to simplify some of the expressions. Sometimes not. Sometimes it's just a mathematical exercise, but sometimes it allows us to help simplify. Our properties or rules for logarithms have the same three for logarithms that we had for exponents. First, we have the product rule for logarithms. It states that the logarithm of a product is the sum of the two or three logarithms. So again, multiplication, because the product is the answer to a multiplication problem, pairs with addition, because the sum is the answer to an addition problem. In general terms, log base b of the argument m times n is the same thing as log base b of m plus log base b of n. So I've taken a product and I've split it apart using addition. Now, what does that look like as an example? For example, if I have log base 5 of 25 times x as my argument, that means that I can split this apart to say log base 5 of 25 plus log base 5 of x. And log base 5 of 25 will simplify. What is the exponent of 5 that gives me 25? Well, 5 squared is 25. So this expression simplifies to be 2. I can't simplify log base 5 of x, but I did simplify that first expression. The interesting thing about these rules are that it works from either direction. We started on the left and moved to the right here, but we can also start on the right and move back to the left. For example, let me switch colors. Log of 5. So if I write log log and no base, we know that's base 10, my common log, plus log of 2. I don't know why my green is giving me so much trouble, is equal to, now if I'm adding the two individual log statements with the same base, I know I can combine them into a single log statement, same base, where I multiply the arguments. So my argument is going to be 5 times 2. Well, 5 times 2 is 10. So that gives me log common log of 10. Well, what is the exponent of 10 that gives me 10? Because my base is here. Well, the exponent of 10 that gives me 10 is just 1. So I'm able to simplify these two individual log statements that I couldn't do anything with separately all the way to 1. Okay, so that is our first rule, our product rule for logarithms. Let's look at the quotient rule for logarithms. Quotient rule is going to talk about division. So the logarithm of a quotient, answer to a division problem, is equal to the difference, answer to a subtraction problem, of the two logarithms. So again, division and subtraction pair because division is just repeated subtraction. All right, let's do a couple of examples there. Actually, we're just going to do one example here. Let's do log base x of, and then my argument is 9 over x, 9 divided by x. So I have a quotient as my argument, which means I can pull that apart. Oh, we didn't do the general term. I'm so sorry, I got distracted. General case, where I have a quotient as my argument, I can break that apart to say log base b of the numerator minus log base b of the denominator. So I'm subtracting out anything that shows up in the denominator. Now to my example. Sorry, I got ahead of myself. I can split this apart. I'm dividing in my quotient, so I can rewrite it as log base x of 9 minus, because division pairs with subtraction, log base x of x. Well, log base x of 9, there's nothing to do with that. Log base x of 9 can't do anything, but right here, log base x of x. What is the exponent on x that gives me x? Well, that's just 1. So sometimes when I expand, this is an example of expansion, or condense, this is me condensing it down to a single log statement, it lets me simplify, but that's not a given. It doesn't always simplify. Sometimes we just work through it and change the way it's written. Let's look at our third rule or property for logarithms, our power rule. The power rule for logarithms tells me that the logarithm of a number with an exponent is the same as the product of the exponent and the logarithm of that number. Now I know it's difficult to read it and apply it, so we're going to look at an example. Here I have log base b of, and then my argument is m to the p power, so I have an exponent. My power rule tells me that I can rewrite this exponent as a product, as a multiplication. So I'm going to bring that p out front and multiply it times the statement log base b of m. So anytime I have an exponent, I can bring it out front and write it as a product. For example, I have natural log of 3x squared. 3x squared is my argument. Now we're not going to just apply the power rule because I have an exponent here, but the exponent just applies to the x. The only base here is the x, not the 3. So I can't pull it out in front of this product that's in my argument. But I can apply my product rule and split that up. Natural log 3 plus natural log x squared. I chose addition because multiplication pairs with addition. That's my product rule. We've got ln, that's natural log base e. Cannot simplify here, cannot simplify here, but I can use my power rule. Here's where I use my power rule. I've got natural log 3 plus 2 natural log x. Again, sometimes things don't simplify, I just rewrite them. This is one of those cases. So I applied the product rule first, and then I was able to apply my power rule. I could not start with the power rule because this 2 only has x as the base, not 3. So it does not apply to this entire argument, just this piece. Okay, so we have lots of practice here that we're going to do together on these next 2 pages, and we're going to learn about the change of base property. So let's approach some of these practice problems together. In our first example, we have a quotient in my argument. So we're going to use our quotient rule, which means we pair division with subtraction. That gives me log base 3 of the numerator, 27, minus log base 3 of my denominator, 4. So I have expanded from 1 log statement to 2 log statements. Now I look at those 2 log statements and I see where I can simplify. I can simplify the first one, can't do anything about the second one. What is the exponent of 3 that gives me 27? Well, 3 cubed is 27, so the answer to this logarithm is 3. And then I have minus log base 3 of 4 because that expression does not simplify. All right, let's look at number 2. In number 2, we have a product in our argument. We are multiplying 3 different things together. We're multiplying 3 times x squared times y. Now we know how to deal with 3 times x squared because we just did it. So let's separate this out because I have 3 factors in my argument. I'm going to have 3 separate log statements. They're all natural log base e. And then I look at those 3 log statements and I determine that I can do something else to this second one because of the power rule, because I have that exponent there. And that's all I can do. I can't simplify. I just was able to rearrange and rewrite. Number 3, log base 3 of 9 to the x. 9 to the x is my argument. I'm not multiplying or dividing, but I do have a power. So I'm going to apply the power rule, which gives me x times log base 3 of 9. And then I look to see if I can simplify further. And I can, because this is a nice integer answer for me. What is the exponent of 3 that gives me 3? Well, 3 squared is 9. What is the exponent of 3 that gives me 9? Sorry. 3 squared is 9. So that is x times 2, or just 2x. So that one did definitely simplify nicely. All right, when I look at number 4, it's log log, which is base 10. I've got the square root of 3. What can I do with that? Well, I can rewrite a radical as a rational exponent. So that's what I want to do. I'm going to rewrite my radical as a rational exponent. It's a square root, which means it has an index of 2. So 2 will be the denominator of my exponent. So I have log of, and then my argument is 3 to the 1/2 power. Well, log is base 10, 3 to the 1/2. I can use my power rule here. So I have 1/2 log of 3. Still base 10. There's not anything else I can do with that if I want to keep this exact. Pay attention to what my MATLAB says. This is my exact answer, expanded as much as I can. However, I have a button for this on my calculator. So right now, so we can practice with our calculator, I want you to do this in your calculator and round to 3 decimal places. So I'm going to use my common log button, log log, and order of operations, I'm going to do log of 3, enter. That's the result I get. and then I need to take half of that. So I can do this a couple of different ways. I can multiply times 1/2, I can divide by 2, or I can multiply times 0.5. I'm going to choose to interpret 1/2 as 0.5 and multiply that answer times 0.5, which gives me this decimal that does not terminate or repeat. Like I said, I want you to round it to 3 decimal places. Make sure you round correctly. If I look at my 3rd decimal place, I have an 8. The next term is a 5, so that tells me to round up. So this is approximately 0.239. 239 thousandths. Okay, number 5. Log of 100x. Log, 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 common log is base 10. I have a product in my argument, so I'm going to use my product rule. Multiplication pairs with addition. So when I split it apart, that's what it looks like when I expand it. I look at both of those log statements and see that I can simplify the first. Base 10, what is the exponent of 10 that gives me 100? Well, that would be 2. 10 squared is 100. So I have 2 plus common log of x. Number 6, I have a quotient in my argument. Division pairs with subtraction. So I take log base 4 of the numerator minus log base 4 of the denominator. I can simplify that first statement. What is the exponent of 4 that gives me 64? Well, 4 cubed is 64, so I have 3 minus log base 4 of y. Number 7, I have a product in my argument, so multiplication pairs with addition. Log base 5 of 7 plus log base 5 of m. Not anything I can do with either one of those expressions. I have expanded, but I can't simplify any further. On the next one, I have an exponent in my numerator, but overall here I have this quotient going on. So I'm going to start by using my quotient rule and pairing my division with subtraction. So I've got natural log of e to the 5th minus natural log of 11. Well, I can simplify here because of my power rule. So that becomes 5 times natural log of e minus natural log of 11. And now I can do something about this natural log e. Natural log is base e. What is the exponent of e that gives me e? Well, that would be 1. So this first expression is 5 times 1, or just 5. Minus my natural log of 11. And then on number 9, I have natural log of the cube root of x. Well, remember that when I have a radical, I can rewrite that with a rational exponent. When I had square root, my exponent was 1/2 because the index is 2. When I have cube root, my exponent will be 1/3 because the index is 3. So this is natural log of x to the 1/3 power. I don't leave an exponent there. I use my power rule so that I rewrite it as 1/3 times the natural log of x. There's nothing else I can do there, so I'm done. That was all expanding logarithms. That was expanding. The next 4 examples are condensing. So I'm taking more than one log statement and rewriting it as a single expression. On this first one, I have common log of 25 plus common log of 4. Can't simplify either one of those statements, but I can rewrite this addition of 2 log statements using my product rule by multiplying the arguments, which would give me log of 25 times 4. Well, 25 times 4 is 100. Log of 100. Well, common log is base 10. What's the exponent of 10 that gives me 100? It's 2. So I was able to completely simplify that. Remember, though, that sometimes we can't simplify at all. Sometimes we're just rewriting in different terms. Let's look at this next one. Number 11 has 2 times the natural log of x plus 1/3 times the natural log of x plus 5. Now the first thing I want to address is this argument x plus 5. We don't have anything for addition inside an argument. Addition inside the argument, it just is what it is. We can't rearrange, we can't reinterpret, we can't rewrite. This argument is x plus 5. Don't incorrectly apply your product rule. The product rule will be applied here, but first we need to apply our power rule to deal with that 2 and that 1/3 out in front. We can't do anything until we apply the power rule. So our next step would be natural log of x squared plus natural log of x plus 5 to the 1/3 power. Now x plus 5 to the 1/3 power is the cube root of x plus 5. So that's an option for me, but you don't have to go there. What you do need to do next is say, okay, I'm adding two log statements with the same base, so I can rewrite that as a single log statement, and my addition is going to pair with multiplication. So I'm going to multiply the arguments together. So I have natural log of, and then my arguments would be x squared times x plus 5 to the 1/3 power. I can stop right there. I can be done. Or I could choose to rewrite that as, or either one is fine. Natural log of x squared times x plus 5 to the 1/3, or natural log of x squared times the cube root of x plus 5. Either one of these arguments is correct. It's not going to make any difference which way we answer it. My math lab is going to accept it either way. I accept it either way. Okay, sorry, that was a little lengthy. Let's look at this next one. It throws in addition in your argument again. Remember, can't do anything about addition inside the argument. So what we're going to start with is using the power rule on both of those individual statements. So that I have natural log of x plus 6 to the 4th power minus, and I haven't done anything there yet, natural log of x cubed. Now I can think about, now that I've taken care of the power rule, I can think about combining this into a single natural log statement. Subtraction pairs with division. So I start with the first statement. That argument will be my numerator. This argument will be the denominator. So I have natural log of, my numerator is x plus 6 to the 4th, and my denominator is x cubed. And there's not anything else I can do to simplify at that point. Okay, the next one, I have 3 log statements here, all natural logs, so they're all the same base. I'm going to combine these into a single, condense them into a single log statement. Start with your power rule. Apply the power rule to each of those individual log statements as needed, so that I end up with natural log of x cubed plus natural log of y to the 5th minus natural log of z to the 6th. Now, I'm adding and then I'm subtracting. Where I'm adding, I'm going to be multiplying those arguments. Where I subtract, I've got a quotient. So these two represent my numerator. This argument represents my denominator. What I end up with is the natural log of x cubed y to the 5th over z to the 6th. So the things being added go into the numerator, the things being subtracted go into the denominator. And then our final example on this page, 4 log statements, all natural log, so they all have the same base, which means we can condense them into a single log statement. Remember that anything being subtracted is going to go into my denominator. Take care of your power rule first. So let's apply the power rules where we can. That gives me natural log 3 plus natural log x squared minus natural log y cubed minus natural log z to the 4th. Now I rewrite this as a single log statement, all natural log of. The things being added, those arguments go in my numerator. What is being subtracted goes to my denominator. Nothing can be simplified. Okay, we have 3 more examples on this next page. They're more complex examples, and then we're going to talk about change of base property. Just FYI, the last page in your guided notes, we're not going to do together on the video. As with all of the others, if you're in a class that meets as a class on BBCU, we'll do this in BBCU. If you're not, if you're in a fully online class, then do that on your own as practice and contact me with questions. All right, let's finish this page where we have 3 more examples. Condense or expand or condense as necessary, simplify when you can. I want to encourage you to pause your video, do what you can on your own, and then come back for our discussion. All right, so let's work through these 3 problems together. On the first one, we have a quotient. Overall, when I look at this, the first thing I see is that I have a quotient in my argument. So I'm going to deal with that first. I'll say log base 3 of, and then my numerator is x minus 1 squared, minus, because quotient division pairs with subtraction, log base 3 of 9z to the 3 halves. Okay, so pulling it apart, I can do more. I've got a power here that I can pull out front. So I've got 2 log base 3 of x minus 1. Remember, I don't do anything about addition or subtraction in my argument. So this expression is done. I can't do anything else with this first expression. For the second expression, I have an exponent, but this exponent is only on the z. It does not apply to the 9. So before I use my power rule, I have to pull this argument apart. It's being multiplied. Multiplication pairs with addition. So in parentheses, I would have log base 3 of 9 plus log base 3 of z to the 3 halves. In parentheses, because this argument came from the denominator, which means it is being subtracted from this original argument that was in the numerator. So this subtraction is going to distribute to both terms when I split it apart. So keeping in mind that I'm going to distribute that subtraction, we have 2 log base 3 of x minus 1 minus, well, what can I do with this? Log base 3 of 9, I can simplify that. The exponent of 3 that gives me 9 is 2. 3 squared is 9. Then I have minus, and what can I do with this? Well, I can apply the power rule so that this comes out front. So minus 3 halves log base 3 of z. Can't do anything else with this log base 3 of z. So this is fully expanded and simplified, and I'm done with that expression. Let's look at number 16. So anything that comes from the numerator is added, and because we see that we start with this subtraction before we split it apart, anything that comes from my denominator is going to end up being subtracted. Now, hopefully you're getting more comfortable. If you're not, go ahead and put in that extra step like I did right here. But I'm going to go ahead and say, you know what? I can split this argument from the numerator apart, and I'm adding. Then I can split this argument from my denominator apart, and I'm subtracting, because that's the denominator of the quotient. So I'm going to skip what would be my first step and say log base 5 of x cubed plus log base 5 of y to the 4th. Those are the 2 statements that were multiplied in my argument in the numerator, minus log base 5 of 125 minus log base 5 of z squared. Those are the 2 statements that are subtracted because they came from my denominator. They were being multiplied here. When I split them apart, I distribute that negative. Now, what can I simplify? Well, first term, I can use my power rule. So that's 3 log base 5 of x plus second term, I can use my power rule. So 4 times log base 5 of y. Third term, I can simplify. What's the exponent of 5 that gives me 25? Well, 5 cubed. So that simplifies to be 3 minus, and then again with the power rule, 2 times log base 5 of z. That's all I can do. I have fully expanded that log statement. All right, number 17, the last example here that we have. Once again, these two were expanding. This one is going to be condensing. Notice that I'm adding here and I'm subtracting both of these. Let's use our power rule first. Our power rule would give us natural log of x cubed plus natural log of y to the 4th minus natural log of z squared, and then minus natural log of 8 because I don't have an exponent or a coefficient in front of that natural log 8. Now, what is being added together is going to go in the numerator. What's being subtracted out is going to go in my denominator. It's all the same base, all natural log, so I can write it as a single logarithmic expression with a numerator of x cubed y to the 4th and a denominator of z squared 8. Oh, you know what? I should have written that as 8z squared, shouldn't I? Let's go ahead and make that prettier. Natural log of x cubed y to the 4th over 8z squared, because in the correct form, we put that coefficient in the front of our variable. Okay, one last thing to go over in this section is our change of base property. Our change of base property tells us that allows us to estimate logarithms, to get an approximate answer by using base 10 and base e in our calculator. So with the change of base property, we can get approximate values on our calculator by using a ratio. Now, here's how the idea of a ratio works. Before I give you the change of base property, I want to talk to you about a ratio. If you've ever used a concentrate of anything, you've used a ratio. Let's say that I have a cleaner, and the instructions on my bottle of cleaner tells me to use 1 part cleaner to 3 parts water. Now, it doesn't tell me how much to mix up. So I can mix up as much or as little as I need. If I'm just trying to clean my kitchen cabinets, I might use 1 tablespoon of the cleaner to 3 tablespoons of water. If I want to do my floors, my kitchen floor, I may use 1 cup of the cleaner to 3 cups of water. The strength of this little bit of cleaner is going to be the exact same as the strength of this 4 cups of cleaner because I use the same ratio. When I use a ratio, what happens basically is that my units, tablespoon over tablespoon, that's just 1. Those units divide out. Cups over cups, that's just 1. My units divide out. So I get what we call a pure number. Well, that's what we do when we use our change of base formula to solve logarithms for a weird base, like base 5 or base 3 or base 11. We can use our change of base formula. Now, when we're using change of base, that means A is something that's not 10 and it's not E. I set it up as a ratio. I'm either going to use common log or natural log. I don't have to do both. I pick one or the other. What matters is that whatever I use in the numerator matches what I use in the denominator. And then I have these 2 values, my base and my argument, b and m. The base is going to go on the bottom. B for B. Base goes on the bottom. The argument goes in the numerator on top. That's how we set up using our change of base formula. Now, very simply, let's do an example with not letters, but with actual values. So let's say that I need to simplify log base 3 of 7. Well, I don't have a base 3 on my calculator. If I need an exact answer, this is the best I can do. I can't do anything else. But if an approximate answer will work, that is when I can use my change of base formula. So if I'm using change of base, I have two choices. I can use either log over log, common log over common log, or I can use natural log over natural log. Does not matter. What matters is that my base goes on bottom, which means my argument goes on top. Now, I want you to plug this into your calculator. Do it both ways. You're going to get the approximate value, and I'm going to round it to 2 decimal places, 1.77. Now, let me show you how. Make sure we're doing order of operations correctly on our calculators. So if I choose to use common log, I'm going to push common log of 7, enter, and then I'm going to say divided by common log of 3, enter, and I get 1.77 rounded off. If I choose to use natural log, I do natural log of 7, enter, divided by natural log of 3, enter, and I get 1.77 rounded off. The exact same answer, because what I did was set up a ratio where the base values divided out, and I'm left with that pure number, that approximated answer. Once again, this is an approximation. You can only use change of base if a rounded off approximation is going to work.